So what is this course about? We will review some modern topics in condensed matter theory with some goal in mind. And the main goal is that we would like to understand what in many-body theory is specifically quantum. Okay, so usually in a condensed matter system, there are both classical and quantum aspects that conspire together. And we would like to focus our attention on the quantum aspects of matter. So in some sense, the main goal of this course is to understand what is quantum matter. And to this end, we will ask some questions. And so the first question, one of the questions that we'll try to answer is, what is a quantum phase? And a related question, what is a quantum phase transition? Another question that we have is the following. So probably you are familiar with this notion that in condensed matter theory, it's a bit different from the high energy physics or fundamental theories, in that we have this notion of emergence. Have you ever heard about this? This means that there is this very famous paper by Anderson says more is different. So the fact that we have a many-body system doesn't make it just bigger, but really different. And the main thing that emerges is order. And we would like to understand what is quantum order. So a way for a many-body system of having some ordering that is specifically quantum mechanical. Another question is, what is the role of quantum correlations? So all these topics will be seen in I hope, in the first 2 weeks, whereas in the third week, we will be mainly concerned with one topic, which is very important. And so before writing it down, I want to ask you a question. What do you think is the most common and universal physical phenomenon? The most common of all. The one that is before your eyes all the time. So something that people might have noticed 3,000 years ago. Try. So what do you think is the commonest thing that you see? Sorry? Yeah, light is fairly common. However, there is also darkness, right? And so light is fairly common, but what I'm talking about also happens in darkness. So the commonest of all the things is it's a very wide class of phenomena called thermalization. So whatever physical system you have, you can experience that the situation in which it is either a thermal equilibrium or it is in some state that is away from equilibrium and it evolves in time, but then ends up in thermal equilibrium. And in fact, there is a beautiful poem by Heraclitus that was written 2,600 years ago that states this thing. It says the cold thing become warm, and the warm become cool, and the damp things become dry, and the dry become damp, moist. So people noticed that a long time ago. And we would like to understand how does thermalization happen in a quantum system. So now all these topics require the fact that we are in a quantum system, but also in a many-body system. Okay, so none of these, apart from quantum correlations that can happen also in a few-body system, but the rest, none of these would make any sense for a quantum system of a few bodies. Okay, so we need a many-body system. With large capital N particles. And we want N to be large. This is because ordinary materials have, a large number, 10 to the 23 or more particles, but also because regardless whether they are realistic materials or not, all these interesting phenomena happen in the large N limit. So typically what we like to do, like you do in statistical mechanics, is to take the thermodynamic limit and go into infinity. So the first thing I want to discuss today is that the thermodynamic limit is something that you have to be very careful with. It's not something that you can naively take, okay? That you can always, and without thinking, take the thermodynamic limit. And the second thing I want to say about the thermodynamic limit is that also, what does it mean? Okay, since in nature there are never an infinite number of particles in any physical system. So what does it mean? What happens if we have a phenomenon that only happens mathematically in the thermodynamic limit? Okay, so in what sense it has a physical relevance? So the point of view that we'll adopt in this course is that the thermodynamic limit is a sort of convenient simplification to deal with the asymptotic properties of a finite system. Okay? But we must have in mind that the system is finite. So the thermodynamic limit can capture the essence of the properties when n is very, very large. But what really matters is how whatever behavior we are looking at scales with n. So scaling for us is important. In particular, we are interested in three cases that I will always refer in this way. So if a quantity, no matter how big it is, but it does not scale with n, it's a constant, we will say it's order 1. okay? So sometimes I will refer to things being microscopic, like, and I would say, for instance, if I'm talking about time, lifetimes of something, I will say, oh, this is short-lived. I mean this, okay? So I'm not so much concerned with how much is this number, okay? I'm concerned with the fact that it's microscopic. So order 1 is microscopic because it does not depend on n, right? The system could be small or large. The constant is always the same. Okay. The second scaling that we are interested in is if it is any polynomial in n. Okay. So of course this is a vast class, right? It could be linear in n, could be n squared, n to 100, but it's still all polynomial in n. And by the way, this has this thing is important because if something is polynomial in n, then it can be simulated on a computer. Okay? So in some sense, it means that it is not too complex. And then finally, as you can imagine, there is exponential behavior. Okay. So we are interested in these 3 types of scaling. So you see the thermodynamic limit in which n goes to infinity. Maybe we have some quantity that is also diverging, but it matters if it goes like poly n or xpan. Okay. So we said that we must be careful in taking this limit. And let's try to understand why. Okay. So do you have any idea why something could go wrong when we take the thermodynamic limit? Yeah? Sorry? Yeah, if the limit is well defined. The limit of what, right? This is what we have to. So we take the limit n going to infinity. We're taking the limit of some quantity. And the quantity that we are interested in could be the free energy density or the energy density. So one problem is that so the energy density, so does this limit exist? So we have the energy of our system that depends on n somehow, and the volume of our system that depends on n. This is the energy density. So we say that the thermodynamic limit is well defined if this limit is some finite number. Because in nature, we cannot have an infinite energy density. Okay? In a finite region of space, we must have finite energy. And then there is a second concern. So this actually is a concern that we must always have also in classical condensed matter theory. It is not specifically quantum. But also we have a quantum concern. So the quantum concern is a bit more subtle, and it is the following. So it's initially a mathematical concern, but then it turns out that the mathematical answer to this thing actually places a very strict requirement on what type of physical systems we can consider. So the quantum concern is the following. So because we are in quantum mechanics, our system will be, we will consider in this course mostly closed quantum systems. Okay? We will spend some words about open quantum systems later, but mostly we'll be concerned with closed quantum systems, which means that they are defined by a Hilbert space and a Hamiltonian on the Hilbert space. Okay? So as you know, basically the Hilbert space is a linear space in which you have a scalar product such that every sequence converges, every Cauchy sequence converges. So it must be complete in some way. Now look at this thing. Let me give you an example. And then as homework, you can try to generalize it to generic states in the Hilbert space. So imagine that I have two quantum states in a Hilbert space with few degrees of freedom. So let's start with just 1 degree of freedom. So this is a quantum state, and this is another quantum state. We have one particle. And imagine that these two states are very, very close. So this means that their overlap is almost 1. Okay? So I write it in this way, 1 minus epsilon. Now, what does it mean that we take the thermodynamic limit? So first of all, how do we build the Hilbert space with n particles? So in this course, we will be mainly concerned with Hilbert spaces of what we will call spin systems in a generalized way. And the first requirement that we have is that the Hilbert space has a tensor product structure. Okay, what does it mean? That I can write H like the tensor product of many Hilbert spaces. And at least for the time being, let me also require that each of these Hilbert space is finite dimensional. Then we will see what happens in the infinite dimensional case. But let's start with something that is finite dimensional. Okay? So by the way, given some Hilbert space, is this always possible to decompose it in a tensor product structure? Or you know, or it is a real requirement, this one? It's a strict requirement or a loose requirement? What do you think? A metric? No. It's a simpler thing. It's the fact that, as you can see, when you have a tensor product, the dimension, so let me call this di, the dimension of H must be the product of the dimensions. So if this number that I will call n cannot be decomposed, you know, like this, it cannot be factorized. Yeah, so then you cannot have this tensor product structure. Right? So this is a very strict requirement. Most numbers cannot be factorized in any way you want, right? They have their own factors.
But you could just embed it, right? You could just embed it in a larger Hilbert space, and it's treated as some effective subsystem, right?
Well, then that's another story. Then what it means is that the one that is a tensor product structure contains states that are not effective, right? That you wanted to be out of your Hilbert space. So it's a bit cheating, right? Mm-hmm. Yeah. Okay. So we have this thing, right? So what is a base? So if these are basis states, if this, forget about basis states. Let me pick some easy state in this Hilbert space, so that it has this So let me generalize this situation to a many-body system now. So we have phi that is a simple state that it has a tensor product structure of many phi I. Okay? I have, for every particle, imagine that our Hilbert spaces are all the same. For every particle I have, every particle is in the same state. Just as an example. Actually, it doesn't matter if it's exactly the same state or not. Just matters that it is a tensor product. And the same for psi. Okay. So what happens now to this product? So you see, when you take this product, you see that this is smaller than 1 over minus epsilon mean, where epsilon mean is the minimum of all epsilons, because I'm requiring that each of these copies of the states are very similar. So even if I take the best case scenario, in which I just take the smallest difference, this thing goes in this way, which in the thermodynamic limit goes to 0. And this is very generic. Actually, almost any two states, so not only product states, almost any two states in the Hilbert space. So let you try to do it as a homework to show that unless the coefficients of the superposition have some special form, but generically this will happen, are orthogonal. So which means that your scalar product is not well defined. All states are orthogonal. And Cauchy sequences are not always converging and all that. So this means that this object that we would naively define the thermodynamic limit in this way, we just take infinite copies of our Hilbert space, doesn't work. Mathematically, it doesn't work. So of course, von Neumann found a solution to this stuff. And the solution that he found was that there is a sophisticated way of doing this that would take us too far. So I'll give you the physicist point of view. The sophisticated way is called, C-star algebras and things like that. But the meaning of it is that instead of taking only, all the states in here, we just take those states such that their scalar product is well defined. Okay, so we don't take, so it goes to 0 only if it is already 0 before the thermodynamic limit. Otherwise, it's finite. So how do you do that? How do you build this set of states that are very well defined? So you start from a reference state. Okay. And then you act. So how can you build states in a Hilbert space? So you can always start from a reference state and then act on them with some operators, because operators take you from states to states, and then making superpositions of them, right? A fancy way of saying this is that we operate with some algebra on it. It's just this. We have some operator algebra. We can operate on them and take superpositions. Now, look, if this algebra has this property that is called quasi-local, so it means that we have this algebra A, and we have some operator that belongs in A, and we call it quasi-local. If it has this form, so A acts like the identity. So let me first say where it acts not like the identity. It acts like some operator, let me call it F, on the Hilbert space Hi, and like the identity on the complement of this Hilbert space. First of all. So what do I mean by this? So remember that our Hilbert space is the tensor product of many, right? Now, all these indexes, I can split them in two sets, right? So I can have the indexes that belong to a subset I, and those that belong to the complement of it. Okay. And B, the number of points in this set, let it be finite. Whereas the complement now, when we take the thermodynamic limit, this one must be infinite, right? Because we have an infinite number of Hilbert spaces Hi. So I just pick any subset that contains a finite number of them. So you see, this operator differs from the identity only on a finite number of let me call them from now on local Hilbert spaces. So the result is that when I apply two operators, A1 and A2, that belong to this quasi-local algebra, and I apply them, or also linear combinations of them, to our reference state, and this defines my states psi A1, psi A2. Do you see that their overlap is equal, or can be anyway upper bounded, by the product of one an infinite number of times, so infinite times, and then the product of other numbers that are something that can be upper bounded by some number epsilon, but only up to this number here that is finite. So bottom line, all the scalar products inside the set of states that are obtained by applying the algebra of operators A on the reference state, all the scalar products are defined. So the real Hilbert space is this guy. So we have learned something, is that if we want to do many-body theory, we need to only consider operators that have a structure like this, that have some locality embedded in them. Yeah?
Why does it have to be tensed with the identity matrix and not, for example, say, just the zero matrix? No, okay, no.
Good. Because doing nothing for a matrix is the identity. Yeah, what? Yeah.
So here let's say you construct out, it does not cover the whole space.
No, it doesn't cover the all infinite
Yeah.
tensor product, no.
But how do you justify that those states are not physical? or those states that like they might be physical but just
well, if they are physical, we you know, because so think about it. All the structure in quantum mechanics, all what we mean by physical, like for instance taking expectation values, comes out from the mathematical structure, you know, is encoded in the mathematical structure of the Hilbert space in the fact that we can take scalar products, right? Because an expectation value is a scalar product. You can see it like the scalar product between this state and this state. Now, if the scalar product is not defined, then expectation values are not defined, and then in what sense it's physical?
oh, but here it's supposed to choose a different SI reference, then you will confront it differently with it.
Yeah, very good. So this is a very good point. So mathematically, the choice of what is the reference state, we don't care. But this has some physical importance. So for instance, in quantum field theory, people like to take this as the vacuum of all the fields. So this is a physical state, it has a meaning. And then somehow these are it's the algebra of operators that creates excitations. But now you see that excitations must be local, meaning they must be particles. They cannot be all over the place all the time. I mean, you also have delocalized stuff, but if you want everything to be consistent mathematically, you must have a quasi-local algebra. So the rigorous treatment of this matter is called algebraic quantum field theory. And we will not do that, but I wanted to give you a justification of the fact that physical observables must have a finite, they must operate on only a finite number of degrees of freedom at the time. Okay?
Another question. It's just that we can choose a psi reference to just a vacuum state. I suppose that like the vacuum is struck at a false vacuum, then there will be changing from false vacuum to vacuum, and it means that the total Hilbert space structure is changing. So in that sense, like this mathematical structure does not capture those changing of the ground.
Yeah, I agree. Yeah, so these are problems that you do need to address when you deal with those situations. But we will be concerned with a much simpler situation in which, however, no, you have a point. Even in our simpler situation, we must justify. We cannot just say, oh, this is the reference state. So let me put it this way. For us, any choice of the reference state is good if it's something that we can prepare in the lab. Okay? And then we must be careful whether, to different choices correspond completely different Hilbert spaces. This is actually a very important point, and we will get there at some point. We will see that it really plays a role in condensed matter. So thank you for this. So there is some locality. One of the points of view of this course is that many of the most important properties in quantum many-body theory come exactly from the interplay that there is between considering extended systems and the fact that there is locality. So that all the observables must be local, which implies that also the Hamiltonian, in some sense, must be local. Now we will see exactly in what way. So locality right now means that all observables have what we say finite support. So what does it mean to have what is the support of an operator? Like in this case, it's the Hilbert space on which it does not act trivially like the identity. So the support of A is HI. So although this is an operator on the total Hilbert space, but it is trivial on all these sites, and it is something non-trivial here. Okay? So the non-trivial part is the support of an operator. So locality doesn't only show up in how, this is telling you how many sites, okay? How many of these Hilbert spaces are involved in some observable or in some interaction. But locality also means not only how many, but also how far they are, okay? And so something that we observe all the time is that interactions are in some sense, so let me write it between commas because people have different opinions about this word, in some sense are short-ranged. So all I mean right now is that, they do not persist at infinity. Of course, they can decay in 3 ways that correspond to our scalings somehow. So they can be finite ranged. They can be exponentially decaying. Or they can be, they look almost the same, or a power law. So these are all things that decay at infinity. However, the fact that the thermodynamic limit, so the fact that the number 1, that limit must exist, implies that not all of them are okay. So let me give you an example. So let me consider a system of particles. Okay. Let's consider a system of n particles that are in 3 spatial dimensions. And they have some rho uniform density. And they are in a sphere of radius r. So that, of course, n is equal to 4/3 pi r cube rho. Okay? And now let's choose some interaction potential that is the commonest of all, that they interact with some constant over r, Coulomb. Okay. So if I write it like this, it means that this is x without the minus. It means that they are all charged particles with the same sign, right? So if we compute the total energy of the system as a function of the radius, so of course the thermodynamic limit sending this to infinity is the same thing that sending r to infinity, right? So E of r will be equal to the integral between 0 and r. And then we have this number. A over r. And then the shell So I'm using a Gauss law to compute the total energy. Okay, so if you do this integral, you find a 4 pi square over 15 rho square over R5, which means that the energy over the volume as a function of R is 4 pi over 5 a rho square R square. So you see it's not defined. Sorry. It diverges for R going to infinity, means the thermodynamic limit is not well defined. So a system of charged particles cannot exist in the thermodynamic limit. So this is a problem, because ordinary matter is a system of charged particles, right? So it seems that there cannot be ordinary matter with infinite number of particles, which in turn means if we cannot define the thermodynamic limit, means that also n large is maybe doesn't make sense because the energy density explodes. So where is the catch? Why ordinary matter must have a thermodynamic limit, right? Because we do have stable matter with many particles. Where is the catch?
They can't all be the same charge.
Because they are not all the same charge. So if they were all the same charge, then matter would not exist. Okay. Because they are not all with the same charge, there is a screening, right? So that if you have many charges such that the total charge density, total charge is 0, seen from afar, you see something that has this form. Where this is called the Debye length. I'm sure you've seen this sometime. And now this integral, of course, this converges. However, it converges in a way that it is too good. In fact, we see that we like to have all the particles at very short range. So this is stable from the point of view of the thermodynamic limit, in the sense that the energy density is finite, but the only equilibrium state is all the particles at R equals 0. Well, but at least the thermodynamic limit exists. So in order to prevent that all protons and electrons are together, we need the Pauli exclusion principle, right? So actually, this is one of the main reasons why atom was quantized, to argue that stability of matter was possible. And if you want to see the details of, because this is just a hand-waving argument that if you have quantization, then things don't really collapse. You look at this paper by Lieb. (1973). No, 76, sorry. Even later. So the details of showing that ordinary matter is actually stable, it took a long time to understand, really, to really understand that. Okay, so we are convinced that also if you want to see the generic calculation for any power law interaction, so under which condition this guy gives us a good thermodynamic limit in this spatial dimension, then you have to refer, you can see this argument in the book by Goldenfeld that is in the library, Lectures on Phase Transitions, page 27. Okay, so we are convinced that if we want to be able to take the thermodynamic limit, interactions cannot be too long range. So in this course, we will take, at least most of the time, the simplified point of view in which interactions have a finite range. Okay, so they go up to some distance r, and up to this distance r, they're constant, they don't decay, and then they are 0. So now we have to see how precisely describe these things, that interactions are like this, and that the Hilbert space itself must be local. Okay? So how do we, if a system does not have these properties, then it will not be a physical system. Because there will be not, the thermodynamic limit will not make sense. We will not be able to do anything that can scale with the n. So the way we incorporate this is the following. We so we have this picture in mind. So these dots are our local Hilbert spaces, the ones that are labeled by I. So to each I, we have some Hilbert space I, hi. And we want to say, we want to put some structure such that we can make sense of what it means to be at some distance r. Okay? So the simplest thing that we can do is to put them on a graph. Okay? So I will start putting some edges. Okay. So given a graph, then we give some notion of how far 2 points are. So we will say that 2 points are at distance 1 if they're united by an edge. And then there is a notion of graph distance that says, okay, the graph distance between this point and this point is the least number of edges that I need to cross to get from one point to the other. Okay, we can, of course, give a formal definition of this that I will right now. Okay. So for us, a graph is a set of points that I will call lambda, and a set of edges that I will call E. This is my graph. My total Hilbert space is the tensor product of I belonging to this set lambda of hi. These are the local Hilbert spaces. Okay? Now, let X be any subset in the graph. And we will consider only subsets. So by this I mean the number of points inside the subset that have less than r points. Now, given such a set, I can define the Hilbert spaces, the Hilbert space associated to this subset, which is simply the tensor product of all the local ones in X. Okay? So if an operator O is some operator, let me see, a bounded operator on Hx, we will say it has support on X.
Is X defined as a finite subset? Or
The number of points in X is upper bounded by R, so it's fine. Now let me also give another, I also now want to give a notion of what is the distances inside X. So the greatest distance between points in X is called the diameter of X, which is just the maximum over all the points X and Y in X of the distance between X and Y. Again, this is the graph distance. So just how many edges we need to cross, the minimum number of edges that we have to cross. And the diameter is the maximum distance between 2 points. Okay. So now with these definitions, we want to define a local Hamiltonian. So a Hamiltonian in which somehow we incorporate these things, that we do not have more than R bodies that interact all together, and that the distance at which they can interact is also limited. So how do we do that? We define what is called an interaction map. So phi is some function that takes some subsets of lambda and associates to it some bounded Hermitian operator on the Hilbert space associated to that subset, with the requirement that, as we said, this is smaller than R, and the diameter of X is smaller than small r. And then our local Hamiltonian is just the sum of these guys. So this is the way we incorporate locality in many-body quantum mechanics. The Hamiltonian is the sum of local operators. So you see, this operator is the sum. So this one is everywhere. It has support everywhere. But it can be written like the sum of interactions that are limited. If we need this, because otherwise there would be no thermodynamic limit.
Are those dots in the second pole drawn like is the space or the space-time?
Space.
Yeah, I mean space.
It's space.
When we draw
this is ordinary quantum mechanics, so time is given. Okay, time is the Hamiltonian.
Edges, like, are we making assumption that we are drawing the edge to the nearest neighbor only? I mean,
yeah.
There are
yes, I mean the graph defines space. So this is not, don't imagine it embedded in space. The graph is the space. So if they are, by definition, so the answer is yes, but by definition, we say that 2 points are nearest neighbor if there is an edge. It's a definition.
I mean, I can like draw the edge from like very distant point.
Well, then that means they're not distant.
Yeah, right. It means it's not distant.
So
then
the metric on this space is the graph distance. It is what is telling you whether 2 points are near or not. So do not imagine it embedded in space.
So to define the problem, like we define the graph structure.
The graph structure is absolute. It's not embedded. It's, it doesn't require a space in which to live. It is the space. Of course, you can embed it if you want, but well, it's not necessary. I mean, this is the simplest structure that you can do. The one with the least ingredients, just a graph.
So here you're allowing only the finite range forces. Like, what if it was like exponentially decaying or something?
So right now I am putting, although exponential decay is acceptable, I am putting myself in for the sake of simplicity, in a more restricted situation in which it's finite range. And also I have put myself in a very more simplified situation in which the dimension of every local Hilbert space is finite. So let me give a couple words about these simplifications that we're making. So, which means, what does it mean to do something that is realistic? And on the other hand, when it makes sense to make use of a model, okay? So this is a very important thing that you have to do in theoretical physics. So, because on the one hand, I'm striving to be realistic, right? So by being realistic here, I mean we want to exclude those situations that are not possible. So it's not possible to have thermodynamic limit and extensive behavior and emergence and all that if you don't have some notion of locality. Okay. Now, among all these notions of locality, I am choosing the simplest one not because it's more realistic. It's just because they're all equally realistic, so to speak. Maybe the one with finite range is less realistic, but we could easily generalize the more realistic one. The point being that all the important things that we want to see, we will be able to show them in the more simplified situation, but they do not occur because the situation is simplified. So this is a very important point. If the situation occurs because of the simplification, that's not a good model. So one thing that we will be discussed a lot is this notion of universality. And this is based, in fact, exactly on this. When you write some Hamiltonian, you write some coupling constants, typically. And then you find some results, right? You compute the ground state, you find some result. And then you ask yourself, what happens if I change the coupling constants? So to have that situation, that physical effect, do I need to have exactly those coupling constants? Do I need to have exactly that Hamiltonian? So if this happens, we say that this is a fine-tuned situation. And using a model in a fine-tuned situation is, unless you are doing high-energy theory, in which you think that's the theory of the universe, but for us, it's not good. So we can write some specific Hamiltonian, but then we have to keep in mind that somehow our concern is to show that there is a class of Hamiltonians in which you can change a little bit the coupling constants that have the same properties. Otherwise, it's not good. That is not realistic. So there is no way that in the lab you can realize exactly that Hamiltonian. There are always some defects, some perturbations. Or in a material. It's not a clean Hamiltonian. However, displaying finite range forces instead of exponentially decaying forces is not a problem, because we can prove, just becomes all a bit more cumbersome, that you can generalize to exponential decaying forces. So this is this idealization is good, but asking, for instance, fine-tuned this that would not be good. Other questions? Yeah.
I can imagine the local Hamiltonian in terms of lattice model, but
yes.
I cannot imagine how to define the field theory with this definition.
With field theory?
Yeah.
Yeah, so we'll not be doing field theory. Yeah, so we will be dealing with lattice models.
But this kind of problem may also occur in case of field theory. This is not really restricted to the lattice model, isn't it? Then how can we cure the same problem in field theory?
So case by case, you usually show that by sending the lattice constant to 0, then you can model your things with some field. So you show it case by case. There is not one for all thing. I'm not sure if I understood your question. So there is a field treatment of lattice models, but in this course we will not go there. We will just show the lattice models. In some sense, the real physics, the more real physics is the lattice model. The field theory is another simplification. It's an effective theory upon the lattice model. So let me just conclude with an example. So, and this will be the model that we'll be studying from tomorrow, the quantumizing model. So the Hamiltonian quantumizing model is the following. We have some graph, and then we have the sum of sigma x on all the sides of your graph, minus with coupling constant Gj, and the sum over all the links of your graph, or what we call the Ising coupling, that is just this. So this can be written in this form if the interaction map is the following, that phi associates minus Gj sigma xi for those x that consist just of one side I. It associates this term, this operator, when x is the set that contains just one edge, and 0 otherwise. So with this Hamiltonian can be cast in this form. So you see that here, this is here both x is equal to the maximum number of points that you have in here, and so it's, if you want, I could write it like this. And also the distance, the diameter of x is 1. Only couples at most nearest neighbors. Okay, so this is a local Hamiltonian. Okay, so from tomorrow, this model and its slightly generalized extension called the quantum XY model will be studied for most of this course to understand in a practical example all these notions about quantum phases and so on. Okay, thank you.